right, this is starting Unit 8. We're talking about work, power, and simple machines. And just so you know, this is only the first two sections in Chapter 13. So it's not going to be a very long unit. The last two sections of Chapter 13 go along with our energy unit that we're doing next. So let's go ahead and get started. Let's look at how work is defined. It's the transfer of energy to an object by the application of a force that causes the object to move in the direction of the force. So that means if I'm wanting to move a desk, if I transfer energy from myself to the desk by applying a force like pushing it or pulling it, that means I would cause it to move in the direction I was pushing or pulling, okay? And then I would be doing work. Now, the force must be applied in the direction of the object's motion, and if nothing is moving, then work is zero. The work would always equal zero if nothing is moving. Now, how do we actually calculate work? Work equals force times distance. And if you'll remember, we calculated force in the last unit, and force is always measured in newtons. So it's going to be force times distance, which is W equals F times D. The unit for work that we measure in is joules, and we abbreviate joules with a J. So if I wanted to say that 50 joules of work was being done, I would say 50J, because that would be 50 joules. Now, this is what I'd like you to do. I'd like you to go ahead and practice problems number 1 and 2 on your own using the formula that we've just looked at. See what you can do on your own. Pause the video. Come back once you're ready to check your answers. All right, these are the answers to number 1 and number 2. If you did not get them correct, I want you to stick around with me so that we can go through how I got these answers. If you did get them correct, you're more than welcome to go ahead and fast forward to the next part of the notes. Now, if you didn't understand them or didn't get it correct, let's go ahead and look to see how I got these answers. We're going to erase our answer for number 1, just because that's not what we normally start with. Now, let's read the problem. It says a crane uses an average force of 5,200 newtons. So that tells us right there the force is 5,200 newtons. And it uses that force to lift a girder 25 meters. Meters is used to measure distance. So then it says how much work does the crane do on the girder? So it tells us how much work. That means that's what we're looking for. And whatever our question mark is, that's how we start out our formula. So W equals F times D. So let's fill in our numbers. Force is 5,200 newtons times a distance of 25 meters. Now, once you calculate those and put those in your calculator, you get that work equals 130,000 joules. That's how much work was done. Now, let's go ahead and look at number 2. And it says a bicycle's brake do 1,750 joules of work. So that tells you immediately right off how many joules of work were done to the wheels as the bike moves 14 meters. Meters, remember, always measures distance. So our distance is 14 meters. How much force is applied by the brakes? So that question tells us that's what we're looking for. And whatever we're looking for, we start filling out our formula. F equals what? If you go to our circle, you cover up the F, and it tells you that work divided by distance equals force. So let's fill in our equation or our formula with numbers. 1,750 joules divided by 14 meters. And once you divide that in your calculator, you're going to get 125 newtons. Remember, force is measured in newtons. Now, let's go ahead and get back to those notes. All right, power. Now, what is the relationship between work and power? Power is actually the rate or the speed at which work is done. Another way to say it is how much work is done in a given amount of time. The actual definition is a quantity, which means a number, that measures the rate or speed at which work is done or energy is transformed. Now let's look to see how power is calculated. Power equals work divided by time. Okay, and you can go ahead and draw your circle if you would like. And power is measured in watts, which is a capital W. Now, I would like you to try number 1 and number 2 on your own using the formula to see what you can do by yourself first. And let me give you a hint about number 2. Sometimes you see up here how work is needed to determine how much power is used. Sometimes you will have to calculate work, then get the amount of work done to then plug it into the power equation. All right, so pause the video, do it on your own to see if you understand it, and then resume the video to check your answers. All right, answer to number 1 is 66 watts. The answer to number 2 is 145.73 watts. If you got these correct, go ahead and fast forward to the next part of the notes. If you did not get them correct, then go ahead and stay with me so that we can see how we did these. Now, we're going to erase our answers as usual. And we're going to go ahead and put what we do know. While rowing across a lake during a race, John does 3,960 joules of work. So our work equals 3,960 joules. It says that he does that work in 60 seconds. So we know our time is 60 seconds. What is his power output in watts? So we're looking for the power. So our question mark is the P, so we start with P equals, and it's W over T. Now let's go ahead and fill in those numbers. 3,960 joules divided by 60 seconds. And if you calculate that into your calculator, 3,960 divided by 60 seconds, you're going to get an answer of 66 watts, and that's what equals power. Now, let's go ahead to number 2. Number 2, Anna walks up the stairs on her way to class. She weighs, okay, so 565 newtons, and the stairs go up 3.25 meters vertically. Now, I know meters is distance, right? So we know that that's a distance. It says if Anna climbs the stairs in 12.6 seconds, what is her power output? So we're looking for power. Now, there is a number in here that we actually need to use, 565. And if you'll remember, newtons is used for weight and force, because weight is actually how much force we are placing on the earth. So force is our 565 newtons. Now, we need power, which is work divided by time. We don't have work, but if you'll remember from our last little practice problems that work equals force times distance. So the first thing we have to do is find work, which is 565 newtons times 3.25 meters. And when you enter that in your calculator, you're going to see that you get 1,836.25 joules of work. Now, we can use our power equation of power equals work time divided by time. We can fill it in with 1,836.25 joules divided by the time of 12.6 seconds. And that gives us an answer of 145.73 watts of power. Oop, I went through the watt, I'm sorry. But that's how you get that answer. Now, let's go ahead and finish up our notes. Now, machines and mechanical advantage. Tomorrow, I'm sorry, not tomorrow, but the next video, we're going to talk about simple machines. So we're going to go ahead and talk about, well, how do machines help make our life easier? Machines help us to do work, and they do that by changing the size of the input force, the direction of the force, or both of those. So mechanical advantage is actually a quantity or a number that expresses how much a machine multiplies force or distance for us. So the higher the mechanical advantage, the more the machine does for us. Now, how do we calculate mechanical advantage? What you do, you say mechanical advantage, and it has two formulas. It can either be output force divided by input force, or input distance divided by output distance. Now, one thing you need to know about mechanical advantage, it's not measured in any units. It's just a number. Let's talk about these forces. For mechanical advantage, for example, for a pulley, think about a pulley has a big box or something large on the end of it that it needs to lift up, and you are on the other end pulling the rope. The input force is what you have to do. And always remember, input force starts with an I, and it's what I have to do. Output force is what the machine does for us. And so basically that's what the work output that is, or the force output that's done by the machine. So input is what I have to do. Output is what the machine has to do. Same thing with input distance and output distance. Input distance for like a ramp, for example. A ramp is a simple machine. A ramp, the distance going up the ramp, like the length of the ramp, and I'm going to show you this on a drawing in just a second. The actual length of the ramp is the input distance because that's the actual distance I walk and push something up or carry something up the ramp. The output distance is how tall the ramp is because that's what the machine does for me. Now, let's go ahead. We have some practice problems, but we're going to do these together because they're a little bit different. All right, find the mechanical advantage of a ramp that is 6 meters long and 1.5 meters tall. So this is what I was talking about earlier, but I'm going to help y'all with this to see a visual picture. Now, it says 6 meters long. That means right here. And then it's 1.5 meters tall. Now, this 6 meters is the input distance because that's the distance I have to walk if I'm carrying something up the ramp. This 1.5 meters is the output distance because that's the distance that the ramp actually did for me. Okay? So, to find the mechanical advantage of this ramp, we say input distance, which is 6 meters, divided by output distance, which is 1.5 meters. And as you can see, the meters cancel out. That's why we have no units for mechanical advantage. Now, when you put this in your calculator, you're going to see that 6 divided by 1.5 equals a 4 mechanical advantage. And it's going to be a better ramp than a ramp that had a mechanical advantage of 3, 2, or 1. Now, let's look down here at number 2. Alex pulls on the handle of a claw hammer with a force of 15 newtons. If the hammer has a mechanical advantage of 5.2, how much force is exerted on the nail of the claw? Now, we know we're going to use force because it already has told us force. We just got to figure out what is output force and what is input force. Now, it already tells us the mechanical advantage is 5.2. Now, remember, input force is what I have to do to the machine. So whoever's in the problem, that person, it's what they do to the machine. So do you see that it says Alex pulls on the handle of the claw hammer with a force of 15 newtons? That means Alex used 15 newtons. The person used 15 newtons. So that means we're looking for the output force. So output force, if you cover it up on the circle, it shows you that it's going to be mechanical advantage times input force. It's going to be the formula. So let's go ahead and fill that in with our numbers. It's 5.2 times 15 newtons. And once you calculate that in your calculator, you're going to notice that the output force equals 78 newtons. So output force and input force will be newtons. Input distance, output distance will be meters. And this is how you solve mechanical advantage. Now, this finishes our video for tonight. And what I'd like you to do is a 1-sentence summary. I want you to summarize this whole video in 1 sentence at the bottom of your notes. And I'll see you in class.